Well, isn't that this famous Che Guevara episode in Cosmic Course somewhere?
Sure.
Yeah. Absolutely.
Yes. Okay, so let's get started. Any questions on the main lecture? Everything extremely crystal clear?
Not crystal, but
No, but you do see the methodology that was applied, yes? So this was really the starting point of relativistic cosmology. And the starting point was done, there we go, by Einstein himself. He was the first person to say, you know what? I could use my general relativity to the whole of the universe. He did not come up with frequent equations, but he did come up with all kinds of properties of the universe. For instance, he had his version of the conclusion that the universe should de-accelerate. And then to him, there was something strange about that, because he says, well, either the universe therefore is de-accelerating into this big crunchy thing, he didn't call it that, but that was the conclusion that he could draw, or the universe is expanding, but expanding more and more slowly. And Einstein was not happy with either conclusion. He said, no, but wait a minute, the universe should be just static. It should always remain the same, infinite, but the infinity should not get bigger or smaller. For him, he wanted the universe to be a static thing. And so what he did was he took the equations and he said, you know what, how can I alter general relativity such that it will become a static universe? So he took his equations, his general relativity, and he says, I'm going to alter the theory in such a way that a preferred conclusion comes out. Now this is something you never do in science, yes? You have your equation and it tells you what nature does. If what nature does not agree with experiment, your theory is wrong. And he said, no, I just don't care what the experiment says. I want the universe to be static.
Why did he want that?
I think it's mostly a static reason, but maybe it's also for philosophical reasons, because then if the universe does either de-accelerate back to a big crunch or is now expanding, that means in the past it used to be a big crunch, then you have a lot more explaining to do. Because how did the universe then jumpstart? What defined that early point? Which is still an unsolved issue, by the way. So yeah, so what he did, he took his Einstein field equations and he artificially added an additional term to it. He said, you know what, if I just put this extra number here, then I can make the universe come out static. And then he said, look, I have a static universe now, that's exactly what the universe is. He was wrong. And then he found, not him, but in 1929, when the first measurements were done on the expansion of the universe, those were done by Edwin Hubble, Edwin Hubble found that the universe is indeed expanding. And then Einstein famously said that altering his theory to make his outcome come out different than what the universe actually does, he called that the biggest blunder of his life, because he had in fact already predicted in his original theory before his alteration that the universe should be expanding. He had a beautiful prediction of the expanding universe. He threw it away, and then 10 years later, Hubble measured that the assumption had been correct all along. Now, suppose that you would have on your slip of paper a mathematical proof that the Big Bang happened, and you threw it away because you thought that the answer was going to be wrong, and you even did the most evil thing that you could do in science, namely alter your theory to make a preferred outcome come out. He said that was really the worst thing I could have done. I could have predicted the origin of the universe, the Big Bang itself.
So
yeah, that is so yes.
Big for such an intelligent man.
But later on, actually, it turns out that this extra term that he added to make the universe come out static, the one that was wrong, is actually right. The thing exists.
What?
Wait a second, how did that work?
So his crappy mistake is actually still correct. So this thing that he added to his theory that we now call the cosmological constant is actually a measurable effect. And the effect is well known. It's now been measured up to a certain precision. And we now know that the thing actually exists. So even his worst mistake is better than any of us will ever do. Well, I'm speaking for myself. Yes, that all of you will do beautiful things, but I myself will not do any better than that.
And all of us, everyone. Century of life. Can I have that on a t-shirt?
No, that is very sad, isn't it? Isn't it? So he literally called that the biggest blunder of his life. Damn it. Oh well. So I have an exercise on that. I have a number of exercises, and the question really is just what do you feel like working with? So let me just go through what the exercises are that I have in store. One of them is that we take the Robertson-Walker metric. By the way, this is the metric that I showed with the 3 possibilities. The official name is Robertson-Walker metric. One of them is that we take the Robertson-Walker metric and we do the same sort of playing around with the mathematics as we did in the previous weeks. And we calculate Christophel's, we calculate how things would move through that space, these sorts of things. I think that would be worthwhile to do. The second exercise is actually something that I had briefly done at the end as a demonstration of the power of Friedmann equations. Namely, suppose that you have a universe that is either completely filled with normal matter, but it's cold enough not to have any pressure, or with radiation and the electrodynamics tells you that the pressure is such and such, 1/3 of the energy, and then solve these equations. Now I showed you the solutions, we did not do the solving. So that will be, I think, a nice exercise to work with. So you actually practice with the Friedmann equations. I mean, you know the conclusion, it's t to the power 2/3 and t square root, but it would be nice to see that happen. And then there's the fourth exercise, and the fourth exercise is, let's take a universe and drop a small amount of dark energy in there and see what happens. So that connects to the story with Einstein and his biggest blunder. Now, all of them are of course extremely interesting. It's just which one do you want to start with. There's a last exercise, and that is the derivation of the Robertson-Walker metric. We looked at how it is derived by taking the Minkowski metric and even the spherical metric, and then we said, well, you still have the freedom to put a scale factor in there. So we've sort of done that part. But that you can write this, no idea what's going on, but it's very hilarious.
I'm trying to be silent.
No, that's fine, it's fine. Fun story, I was editing the video of the tutorial of last Friday, the one that we had upstairs. I don't know if you've watched that video. There's somebody, I'm not naming any names, but she is from South Africa, eating a bag of crisps.
I wanted to put in the group chat, next time don't eat crisps or cookies next to the recording microphone.
Yeah, that's my fault. I should have put the microphone somewhere else. But she was just, no, she was very silently sitting there. It's just that it happened to be very close to the microphone, so I was editing the video and so it's not just the crispy bag, I could actually hear her chew. But so thank you, Simon, for trying to be more silent and to be mindful. Okay. Anyway, so the final exercise is the Robertson-Walker metric, but do the full derivation. I showed you that it very much looks like a spherical universe, but there's this a squared divided by 1 minus k r squared to derive that thing. Now that I think I would like to reserve until Friday. It's a mathematical exercise, there's not as much physics in there. I would like to reserve this for physics. So, you tell me, preference? No preference? Watch Gossip Girl?
The most interesting thing first.
Okay, so which one is that?
I don't know, whatever.
Okay, but that's my question to you, you plural. So, are we going to look at the properties of a Robertson-Walker metric? Are we going to look at the exercise that we did during the main lecture? Radiation universe or a matter universe, or are we going to look at the dark energy universe?
Dark energy or the first one?
And then
Maybe the first one.
I think properties is first.
Yeah, me too.
Like it's in a logical way.
Yeah.
I don't know. The second one doesn't sound too exciting.
Well, you know, we have a little less than 2 hours because it took us still 15 of your minutes. So we have a little bit less than 2 hours. With a bit of luck, we can do both.
Yeah.
So let's do this. Here is your line element.
Everything.
dt squared minus
What an evil guy that you are.
Here's your line element. I I can really sit down now because the next part is I think up to you to work out.
I have actually a question. Now looking at the formula, the r squared where you're dividing with, is it just going to be the start radius that you have, or?
That is actually one of the questions.
Oh wow. Okay.
Yes. So you're in good company. First question is, let's calculate some Christoffels. Right? I mean, if we want to calculate how things move in this space-time, we have to do some Christoffeling. I honestly don't know the Christoffels by heart. So how about this? I give myself 10-15 minutes of silence. I'm talking 2 hours now, plus 15 minutes. I'll give it to you guys. Let's see if we can get some Christoffels out, and then we can go into write the geodesic equations. Let's see if we can solve those. But going to be an extremely generous lecture. Here's the general equation for Christoffel symbols.
The one is a beta, right? The rho or the p.
I do not
It's
see
a
that.
beta.
This is a beta, yes. Yeah, sorry. And this is correct. Yes, there we go. Think about the crunchy, the anonymous crunchy South African. There were some Spanish Lebanese influences in that video as well. Crunchy wise.
metric tensor in terms of this.
For the Christoffel,
So,
we
for
use
instance, this one,
use
so
tensor.
if we were to
So the square root of the line element, right?
okay, so
Yeah, that's what I checked as well. I think this one is for my notes.
then once you set
I
the
wrote it down
down
into the
the
score.
the only time you can get non-zero
That seems
terms
weird
when
as
both of them
well.
are the same.
Is it?
Mhm.
No,
So
no.
theta has to be theta.
That's
Just
right.
like that.
Mhm.
And then you look at
Because in here,
what is theta?
also
It's R squared.
So it's only R dependent, so you need to
Yeah.
take the
For the
before
Christoffel.
R.
Mhm.
So if it's both dependent for this one, it should be R and
Sun.
That's why you get.
And you do the Christoffels, you usually use the elements of the metric tensor, not the ones from the line elements.
Yeah,
You
but-
first have to square root everything.
But no, the line element has the metric tensor.
Yeah.
So the metric tensor has already the square in a sense.
Yeah, in
Is
that
that-
form, yeah.
Oh, yeah.
Because it's only when you
Because
No, no,
this
no,
you
yeah.
obtain
you
this
have the definition of a
Yeah,
tensor.
mix it up. I
because
had the
this
wrong
you
word.
obtain by doing
You do the-
metric tensor times dx dt dx dt.
Yeah, I
Yeah.
thanks.
No.
We're doing theta first.
I already done.
I don't know why, but I wanted to use theta. Don't ask me why.
Was that this? Oh, really?
Because
Are
it's
they-
not doing now, so when theta only is not square.
Codes are written
So-
in
Wait, do we do the
Only for
internal
theta,
derivative?
theta. So alpha bit is to be theta.
Yeah.
Wait, alpha and beta both have to be theta, right?
For which one?
If you are taking the derivative of theta.
You're gonna take the derivative in terms of theta. and
Like
then
if you have,
conjugate it.
if you all this into a
From the
Christoffel,
hotel,
put
you see what
theta
happens
upstairs.
For
in
theta, does it have to be? No.
Oh no, alpha has to be equal
This
to
is
theta.
so
is
Easy?
no. I mean it is easy, but it's annoying.
And the other
It's easy but annoying.
version that didn't work is if we got the
Because of the crappy derivatives. Because you have an R
Why does theta, why does beta's theta and alpha's all work?
because you go
And there's
into
still a
this
theta derivative
position.
principle.
This is theta, and then the only way you can derive this with R. So it's dr, theta position. For theta.
I will not lie, I do not know the Christoffels by heart. For this one. The other ones is sort of,
So we don't need to
Yeah.
check this all by heart.
nobody wants it.
Okay,
To know
Yeah,
anything
yeah,
by
yeah.
heart, yeah.
No, I
I
fucked
mean, I know the expression by heart.
Okay.
but then with the double or downstairs, you
You have to do the inverse because it's conjugate here.
can't. That's so.
What's your question? It's literally the same as we did in general. Or am I doing something?
No, I think I'm just retarded.
And then this also has the minus in front.
Wait, we're still.
Right. Because the metric is actually not given by those coefficients, but like minus those
Yeah,
coefficients.
that's true.
Which is another thing that you have to remember. I mean, okay, it's a small thing if you think
It
about
just
it.
means that all of the stuff is still an overall minus.
If you wish, yeah. Okay,
Try myself.
Why do you say that?
Because you have the derivative
TT, which is, yeah, that's zero. And then
Use consensus.
Yeah, it's still still behind from being sick from previous week, so it's still working along with it.
As you can see, related to it.
No.
So V has to be
No, we don't do cos.
We do that.
now we're gonna be able to hear you.
That's
I
what
knew
was
it,
thinking of
I
this
knew
before
it.
you have it happen.
I knew it.
Maybe you should make it relevant that we know who's the cause of it.
Your favorite thing, right?
Yeah, I'm going to call Belgium.
So you calling
Yeah,
yourself
this is-
Belgian now?
This is,
Are you proud to be a Belgian now?
this is general relativity with ASMR altogether.
I think we really should do that one.
No.
Just for fun.
What?
It's because R so that's completely the rest of the just makes assumption.
Yeah, but well,
Now we can do
all the way right.
yeah. Because now we have DOT, which is so you have an extra dependent on time. It is also time, so you've got something in your thing. Not twice as many, just a few. No, I mean,
That's what I'm saying.
okay, I'm gonna start with T.
I just want to first.
Okay.
Because I'm way too retarded.
I will get 3 Christoffels with T upstairs.
Yeah.
Calculate what they are, but
V has to be. Are we assuming that R is independent of T for this R? See, that's why I like this one.
Hey, but actually, you're
From
right.
the inside, that's like I'm just trying to simplify it down as much as possible and then see what happens. That's what I got as well. So,
I have to
So it's
Christoffel with T up. I took it down.
In the T1 there is, in the RR there is A prime missing, no? Because when you take the derivative of the,
Oh
Yeah.
no, that goes for all of them actually.
yeah, in all of them there is an A prime.
Yeah, you're right.
Okay. Yeah.
It's chain of course.
where did you get the
Because if you have T,
Squared, sine squared.
the only place is T.
Yeah,
We can
yeah,
take it on
that's good.
Um,
Also,
in order to denote
I think there should be an overall minus.
Oh sure.
Yeah, because
I-
the,
sure.
yeah. But yeah, we already said that.
But you're
Or
right,
the
it's
old
B.
location where you can take the
No, you're right.
derivative and you see the result. 0, 0, 0, 0, 0.
Okay.
Should probably label mine.
For the people interested, the crystals with the T upstairs are on the board. Derivation left side, conclusions right side. I get 3 crystals with a phi upstairs.
Yep.
Yeah, and they're
It looks super bad. You see.
you call it in.
Yeah, and that's the, if you
Yeah.
switch the low to EDCs, you get the same expression.
Yeah.
Can all the other symbols absolute?
Yep.
One should say that.
Hmm.
Oh, actually, Simon, this line should not be there, I think. Because an overall minus
Yeah,
sign
the
is this
minus-
one. But
Yeah,
There's
that's
also a minus.
that's what I was saying from that one.
No, but there's also a minus in front of the.
yes,
It's like it all goes.
It should be plus.
yes.
Because there's also a minus in front of here. And it's all. And then the minus from here.
So this one.
Yeah.
Why was the, because there was an overall minus sign on the left.
No, that's true.
Wait. Restricted.
That is true.
Yeah.
I
And then the-
erased the derivation though.
Which one?
No, I think Tom is right. I think there is.
Yeah, there is a minus.
Yeah,
Yeah,
yeah, okay.
So-
But for different reasons. Okay, there is a minus. Yes. Well, because with the T upstairs, you can easily convince yourself that the first 2 terms are 0 always.
Yeah.
Yeah.
So you will get this minus,
Mm. Yeah.
and that minus will remain throughout the whole calculation.
Yeah, but you have a -1 from the from the
GT.
the
Yeah, GTT.
Yeah.
Yeah.
So it should not be.
Oh
G.
yeah, this plus
Yeah,
TT,
yeah.
so
yeah,
that
so
gives
it's
you a
gonna be-
minus.
So it's gonna be plus.
That gives you a plus, and this is a plus contribution. Okay, well we happily correct ourselves as we go along.
Yeah.
But you took the differential, but where the a of t squared, where it then becomes 2at,
yeah,
or
I
where
agree.
did the 2 go?
I agree.
Here's a
I'm an absolute idiot.
Actually, I'd like to do this.
It's kind of meditative, right? Calculating Christopher's.
You should have cotangent, I think, right?
Yes, this just drops out.
Yeah.
What are you doing now? Terms 4.
Yeah.
Okay, that's nice.
Okay, the Christopher's with the pi upstairs are also on the board.
Yeah.
Just ridiculous.
Does anyone have the R Christopher's?
Yeah. Kind of.
Because I'm going to leave the theta Christopher's. I think I'm just going to leave them because some of the next exercises says, well, how do things move? And we can just plane decide, and we're going to look at things that move in the fixed theta plane. So we don't have to worry about those Christopher's. I mean, they're there, but let's restrict ourselves to a somewhat easier case, just to save ourselves some time calculating all the remaining Christopher's. Okay. I have not checked them, so I have to trust your judgment. Let's see if there's a democracy here, consensus. What are the R Christopher's? I honestly don't know what they are, which are non-zero.
Which are we starting from? There is RT-TR. No, RT. And it's the same as TR in that sense.
Oh, sure,
Yeah.
of course, yes.
I had A prime over A.
Other people have this as well?
I think I had A prime over A. Yeah.
I honestly don't know. This is not me being didactical. Oh, you have to tell each other. I really don't know.
I'm
I'm
not
happy to
done
calculate it.
calculating
It's
them.
What about the
people upon this. I'm
Good.
happy to hear another. The RR?
Yeah, RR.
Which one is that?
KR over 1 minus KR squared, I think.
I hear KR.
Over the 1 minus KR squared.
Oh, I can see that there was a.
No, not squared in that sense. Only the R squared, because the squared cancels out with another one, so yeah. The squared factor cancels out with the inverse of the metric tensor.
Wait a minute, all the R's, if everything here is R, then these two cancel.
Yeah,
you get only
you're
this one.
left
You
with
get
one.
R derivative of
Yeah.
this guy's R.
Yeah.
So it gives you an A squared.
Yeah,
But it cancels against itself. Oh yeah, I see that. And
Yeah.
then if you would take this guy's
Yeah.
derivative, you get a minus
2R.
KR. Yeah, the 2R cancels the 1
with the
half.
1, 2.
But
Yeah,
it's divided by this thing, so it cancels what the square over the total.
Indeed.
Okay, that's very cool. I believe this. Good. Alright. Any other R Christopher's?
yeah.
Yeah. R theta.
Theta, theta, theta.
Theta, theta. Okay.
R, 1 minus KR.
Oh, sorry, I think I missed it.
Yeah, R, 1 minus KR in brackets.
R minus KR.
R in brackets and then 1 minus KR.
I mean, I'm sure you're saying this right, but I'm hearing it wrong. I hear you say R in brackets,
No,
which I'm
R,
happy to do.
oh no, R bracket,
Oh.
first bracket, then in brackets.
Oh, I see. Okay.
Then in brackets, 1 minus
KR. No, I understand.
squared.
This-
R in brackets.
Yes, R
No,
in brackets.
R,
I mean, I was.
comma, and then in brackets.
Sure, I get it. Okay.
The R is squared, right? Because I think it's the same factor as the 1 minus KR squared.
Why is it squared? No, because you have the derivative.
Well, let's quickly check. If you have the theta theta here, then the only one that can survive is this one. Theta theta, you have to take its R derivative. And the theta theta is. Are you guys sure? Theta theta?
That's
Yeah.
totally
Yeah.
different.
It gives
No,
you.
yeah, this part, sure, but I'm sure this must be a square.
Yeah, that's what I was saying.
Okay. Sorry, I missed that.
R theta R.
Yes.
The crystal is still not there. Because it's R theta theta.
No, R theta theta is right.
No, this is correct. I think
Yeah.
This is fine. Yeah, yes.
Just with this part.
Any more cross crystals as in between?
No.
No. So this should be the whole set.
There
if
is-
we're going to ignore.
There is one more, yeah, for the phi phi.
Yeah.
So R on top phi phi.
That's the R on top 5.
Yeah, but not cross terms in that sense.
What is this one?
Sine squared theta r, and then 1 minus kr squared. No, times 1 minus kr squared.
You're the same.
1 minus kr squared.
Yes, that's right. Yeah.
Now let's ignore the crystals with the theta on top. That just means that in the resulting geodesic equations, I'm going to pretend that whatever is moving in a fixed theta plane. Okay. So that means that if we're going to have our space-time, x, y, z, and as you know the theta is measured with respect to this, it means that let's, just for brevity's sake, only look at things that move in the xy plane. Right? It saves us from having to write down all the theta crystals as well.
That's actually very nice because you see that the metric does not depend on phi again.
Yes.
You can have the killing vector. And the killing vector tells you conservation of angular momentum.
Yes.
It means that the orbit remains in a plane.
That is
in that
very
sense.
true, yes. So it's not just gravity that we're going to stick to theta as constant. Killing's theorem tells us that we can do this.
Yeah.
That's correct. That is correct. In fact, Killing's theorem probably gives you a lot faster the answers here than you would by using the geodesic equations. But anyway, let's do it the hard way. Alright, so exercise A of this exercise was calculate the non-zero crystal symbols for Robertson-Walker metric. Now we did that. Okay, here's an important question. Before we write down the geodesic equations, which we now can, and we can in principle solve them, but maybe you remember from last week that there is this very important step that you have to do before you calculate how things move. You have to identify which observer measures this r that appears in the metric and which observer measures the t. I'm going to give you a second to let this comment sink in.
Wait, can you repeat?
Yes.
Who's that?
You might remember from last week when we looked at the Schwarzschild space-time, the Schwarzschild metric, that we had to identify which observer it was that actually measures the r that appears in the Schwarzschild metric, and which observer it is that measures the t. Do you remember that? We wrote the Schwarzschild metric in terms of somebody's r and somebody's t. Who is that person? And we first had to identify, oh, you know what, that's the guy at infinity who is himself stationary with respect to the black hole. Now, we can do the mathematics, we can write down the geodesic equations and solve those and then find how r, or how particle is moving, how its r coordinate is moving in time, and how his time is moving in time, so it's a time dilation. But it's not going to teach us any physics if we don't know whose coordinate it is, in whose coordinate we are calculating these motions. We have to first identify who is the person who is doing the measuring r and t. So that's question B. Can we find out who does the measuring? We can remove this because we have our crystals that are necessary. You understand the question, yes? Okay. So we have to, yes. We see here that this metric, this line element, is written in some person's radial coordinate and some person's time coordinate. Who is that person? In the Schwarzschild space-time was the guy at infinity, he himself being stationary with respect to the black hole. That was the guy in whose coordinates the space-time metric was expressed. Who?
And in time you can see. directly, no? Because if you set all the spatial parameters to derivatives to 0, so you'll assume that the observer is static,
Okay.
then you'll have d tau squared equal dt squared.
That is interesting. Okay, so apparently, if you take some observer and you say, you know what, that observer is not allowed to move, so he does not move in this, and this coordinate, then that means that d tau apparently equals dt. And as you know, d tau is the amount of time that passes for the observer for which you filled in the details. And apparently, that observer is the guy whose time is written in the space-time metric.
But where are the coordinates measured from? In the sense, like, the guy who's not moving with respect to what? The observer.
No, that is a good question. That is a good question. I'm going to give that back to Leonis. The question is very correct, because let's go back to our Schwarzschild example of last week. There we could say, you know what, if we do play around a little with the line element, we found that the person at infinity who himself is not moving with respect to the black hole, that person's time is the time that appeared in the Schwarzschild metric. Okay. Now we also find here that if you have some observer who is not moving, then you will find that it's that guy's time that appears in the Robertson-Walker metric. But in case of a black hole or Schwarzschild space-time, you could say, you know what, not moving with respect to the black hole. Now, what is the object with respect to what you are not moving? We put in that somebody is not moving, but we didn't never specify with respect to what. So I'm curious what you would think. It's a very good question, though. It's important to think about these things, because otherwise, whatever we're going to find r or t or theta, if we don't know who is doing that measurement, the resulting expressions are meaningless, physically meaningless, mathematically sound, physically meaningless. So, okay, it's a guy who is not moving, but there's no black holiness or something from which to define the not moving. So, it's a super good question, by the way, and I'm extremely curious who, based on the lecture of earlier today, can come up with an answer.
Doesn't it depend on k then?
No, because there's no k in there, is there? Because the non-movingness is going to give you 0 regardless
I
of
was
k.
thinking about r.
Yes,
So
but
the question is with respect to what does the observer not move?
yes. Yeah, that is exactly the question. With respect to what is the person not moving?
I mean,
easily
would say the center of the universe, right?
Yeah, but you see that
That
that's
doesn't really exist, so that doesn't make much sense.
If there's one thing that the cosmological principle tells you, that any point in the universe should give you the same answer.
Is it with respect to the stretching, in the sense?
Yeah.
No, but the stretching is the same everywhere as well, isn't it?
But if you're standing
Yeah,
still,
and
the
it's
stretching
also in
should
all
be the same in all
directions.
directions, maybe.
That is a good point.
Yeah.
Because if the stretching happens in all directions, in the same
And
way,
same
but
way,
you move along with one of those stretching directions, then you're apparently you're breaking the cosmological principle. So there's a hint there. So you're not moving with respect to the stretching. Okay, that I agree with that, but maybe we can put it into more physical terms.
But how would you know whether how it stretches? Because everything it moves, so everything might as well just be moving into the same direction as you do. And then if it stretches, even though you're moving into one of the stretchy directions, you would never know.
No, you would. I mean, at the moment that you move along with one of the stretchy directions, that it means that a point in the back of you will stretch away from you further than a point in front of you.
Yeah, but if all the points move just with the same velocity that you do.
Yes, but they don't. If you start moving with, make this a stretchy material, yes, on which you have painted a grid.
Well, yeah, but you assume that you can see the painted grid, which you don't.
No, we do, because we have defined some person's coordinate system.
It's like when you're standing on a balloon, you know, you blow up the balloon and you stay on one point, everything goes further away at the same rate. But if you start walking on the balloon, then even though everything expands at the same rate, like this stretches less fast from away from you than the others.
I was just wondering, because that sort of assumes that you know that the grid is still, and then you can say, oh well, I'm still like I'm not moving in respect with the grid, but it could just as well be that all the points on the balloon are moving, and you're just moving at the same speed as the other points are moving and then the stretching is still, that's what I know.
Okay, but that means that we haven't fully answered the question then. Right? We're still...
I mean, I'm not sure, but I just don't see how you would
I
know.
understand the objection. It just means
Like,
that
it seems circular, that you would say.
I understand. So that means we need something to break the circular reasoning here.
I mean, I'm not sure if there is something. Maybe just answered it and I don't get it, but it just seems like, oh, we're not moving in respect to the thing that's not moving. It's like, yeah, I guess. Well,
So what did we put into our physics to end up with this thing? We put the cosmological principle in, yes? Okay, and then we said something about... No. Let me rephrase the question. In the black hole case, we needed some material object with respect to which we could say that we were moving or not moving.
Mm.
Any material objects in sight in this particular case? Really? No? Cosmological principle gave us two pieces that we could feed in the Einstein field equation. This curvature, space-time metric itself, and this other thing.
Yeah, the T.
The gas.
Yeah, the big
gas.
T.
Yes.
Yeah.
You're standing still with respect to the gas. The gas not flowing by you.
Yeah, but how would you see the gas of the universe? What is the gas of the universe?
The gas of the universe is just a metric distribution. Yes.
Yeah, but then Felix' point still holds because imagine that all the stars and planets are just moving as well.
No, okay, listen.
You have to assume that they're standing still with respect to the
No,
stretching.
yes, but that relates back to what does this give you? This gives you the how things are moving with respect to gravity, how things are moving in the space-time. Yes?
Mm.
If they're moving for some other reason, that would be due to other influences.
Yes.
Okay. But
imagine we were in a spherical space. Well, I mean, it probably doesn't really work in a spherical space-time perfectly, but just for example, could not everything be just rotating around the space-time?
Yeah, that's the point. You have to assume that the things that you're seeing, like planets and matter and stuff, that they're stationary with respect to the stretching, sort of.
As a whole.
You know? Because if everything is rotating, then Felix' argument holds, then you will not know, you know?
But it's just like in gas, you also have particles with momentum and moving, but you don't choose one.
I think
Yeah,
you
yeah,
assume
yeah.
the
But you could
conservation
have
of,
gas flow.
or the overall
You can
momentum
have
being
gas
zero or
flow,
something
only
like
if
that.
you have
no, but remember, we're looking at a very
not
big
a
scale where all the local flowing of things are not being looked at.
Yeah.
You're looking at it in its totality. Yes.
Okay.
Yeah, I understand. Like, it makes
Yeah.
that's what I thought as well. I didn't
Well,
think
that's
Felix'
not-
argument
that's-
first.
that's
Oh,
make
but
it
yeah, I think the fact that we're considering the whole universe makes it particularly hard because you cannot exit, like you don't have any reference.
Considering the fact that you can't ever
Yeah.
know all the movements of all
No,
particles.
but you don't need to, because by definition
Exactly.
we've zoomed out enough that you're not tracing the
Yeah,
individual
exactly.
flowing
That's what I
parts.
tried to say.
It's the net amount of motion of these particles.
But you're assuming that the net amount of motion of the particles is zero.
No. I'm saying no. That depends on how you yourself are moving. Listen.
Okay, but then you're saying if I'm not moving,
Yes.
the amount of motion should be zero.
I'm saying that that if you have a gas, it could be flowing in this way or that way. It has a certain net flow, so don't look at the individual particles. The cosmological principle says zoom out, zoom
Yeah.
out, so that the total thing has a net
Okay.
amount of momentum. How much that momentum is depends on whether you depends on what coordinate system you are. You could choose a coordinate system in which it is zero, the net momentum.
Yeah.
You could also choose a coordinate system in which these particles flow in your face, the net amount. This just says, of all the possible observers that you could have been,
Yeah.
take a coordinate system in which this net amount of gas is not flowing.
Okay.
And maybe some confusion lies in that some of you might think, you know what, but the gas is flowing or not, right? So there is some flowing, and then I decide whether I'm going to move along with it. No. How much of the flowing you see depends on how you are defined, in what coordinate system you define yourself with respect to the gas. You're choosing the coordinate of all the possible coordinate systems you could have chosen. You're choosing the one in which the gas, its net amount of flow is zero.
that the same as saying the center of mass of the gas is not moving with respect
That
to
is very correct. You can also say, I mean, the center of mass of this system.
Mm.
That is also correct.
Yeah.
I mean, that makes sense to me. I still don't understand why that means that you are not moving yourself. Because, I mean, yeah, you, by definition, you define yourself to not be moving.
Yes, but that's all there is there in relativity. You can only define your motion with respect to something else.
There is no absolute motion ever.
So you have to define your motion or non-motion with respect to your surroundings, and we're choosing that one coordinate system that has a zero motion with respect to its surroundings. If I can make one comparison, maybe to drive this point home. Supposing you have a river, yes, and the river has a net flow of V with respect to the what is it called? The Dutch people, help me for a moment. Looking for English word. Hoever. The bank. Thank you. Yes. So suppose that you have a net amount of flow of the river with respect to the bank. Yes. Then you can say, you know what? I'm going to be a person, and I'm going to see this river flow, or I'm not going to see it flow, depending on whether I'm going to move along with this V or not going to move along with this V. That is a very objective way of stating, because there's a third thing with which you can compare yourself, or a second thing, namely the bank. Suppose that you have a situation when there is a river, and there is no bank from which you can find whether the river is flowing or not. But there is water, yes? Then depending on whether you're going to be this guy standing still with this V, or some other guy who's moving along with the V, you will either find that the river is flowing or not. Who is the correct guy? Who is the guy who sees the actual flow? No, well, both of them are correct in their own coordinate systems. As long as there's no second referee here, the bank, to tell you whether the river really is flowing or not, both of them are equally correct. And the only thing that I'm saying right now is, both of these are in principle okay to use general relativity, but the one in whose coordinates this metric tensor is described is the one that flows along with the thing. Okay? I can define many people, this one moving that way, that one is doing somersaults. All of them will see the flow in a different way. This guy measures a certain T and R, this guy measures a certain TR, this guy measures a certain TR, this guy measures a certain TR. Which of the T and R is the one in which the flow is expressed? That's this guy's.
Yeah. I think the key point is the zooming out, the fact that we didn't
Well, yes, I mean, we are assuming, that's the zooming out part, that the individual, we call this actually in astronomy, we call it peculiar motion, the motion of individual particles or galaxies or whatever in the universe, not due to the stretching of the universe, you're going to ignore those, because you're zoomed out enough. Is that point clear?
Yeah.
Good, okay, so we now know that whose T is this? It's the time as measured by the person for whom the Friedman gas is not flowing. So that's as close to being stationary to the Schwarzschild black hole as you can get. You're now stationary with respect to the overall gas, the net momentum of the gas. Okay, so we know whose time it is that we're measuring.
But I have another question. Like, once you know who's measuring the time, you also must be measuring the other coordinates, or not necessarily? In the sense that if you know that the time is the one from that person, can the other coordinates come from another observer?
Yes. If you are an extremely evil teacher, then or somebody else asking you a question, he could have two bookkeepers. One
for something.
Who with respect to who the time is measured, and the other person with respect to who the position is measured. So it's not obvious that the R that we have there is the R as measured by that same guy. So let's investigate that as well. That is in fact the second question now. Whose R is that? Whose position are we measuring? If we don't know this answer, every calculation that involves an R will be physically meaningless. So we need to find out whose R it is in which the Robertson-Walker metric is expressed.
Isn't it the R just saying plus T.
So that would be the person who is standing still with respect to
The glass is
okay.
falling.
well,
I think there is an extra constraint though, because of the factor in front of dr squared.
this one.
Yeah.
Yeah.
Yeah, that's going to make it somewhat abstract.
I mean, you have to make it 1 if you want to have dr equal dr.
Exactly.
Yeah, exactly.
Now, let's start by taking a person with respect to whom the gas is not swirling.
Yeah.
Okay, so theta and phi are going to be constants. So the observer for whom this Friedman gas is not moving in angular direction. I'm switching to ds now, and you understand why, right?
Mm-hmm.
It's because we're going to measure distances. And ds squared is all of this with an over minus sign, but as you remember, measuring distance means measuring front end and back end, or whatever it is you're measuring the distance of, the length of, measure at the same time. So by definition of measuring a distance, dt is going to be 0. Then all of this with an overall minus sign will give you a squared, 1 minus kr squared, dr squared plus a time. In fact, let's not even write down the rest. Let's take the guy for whom the gas is not swirling. I'm just trying to get my ds in terms of only dr, so I can read off what dr means. So apparently, in order to get there, I have to assume that this gas, that observer does not see the gas swirl around him in theta or in phi direction. Then I would get this.
Mm-hmm.
Here's good news, I can do some square rooting now. Well, ds is not dr yet, so yeah, so close, so close. If only I can find dr is dot 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 dot, then I would know who measures the r coordinate. Boom.
You're missing the square,
Yeah.
I think, as well.
You're missing a square on
On the
Oh, okay, yeah,
Yeah.
sure. No, you're right. There we go.
Yeah.
Yes, 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 yes. Ha!
Just the same. I don't know why I never
So ds is what somebody would actually measure if you would take out a measuring stick or something like that. dr is whoever that person is in whose coordinates radius is expressed in the Robertson-Walker metric. That's his distance. And they're obviously not equal, right? This is what a particular person would actually measure. It would, you do a measurement with the measuring rod. It's curved by space-time, nothing new there. And this is the coordinate in which the Robertson-Walker metric is expressed. And they're obviously not the same. So it sort of looks as if there's no observer who actually measures dr. This is what observers measure at any position at any moment in time in space-time. And this is what the coordinates in which the space-time is expressed. And they don't seem to be equal for, right? I mean, ds is not dr. So it seems that there's no observer when he puts out his measuring rod would actually measure dr. There's always this crappy factor in front. Unless, of course, it just happens to be a flat space-time. K is 0. So, okay, well, let's fudge a little. Let's take the K 0 option. Then I will get that dr, the coordinate in which the space-time is expressed, is given by 1 over a times ds, where the s is what people would actually measure. Still not the same. Yeah, or it has to be 1. Well, that's correct. If as a second thing, it just so happens that you look at the moment in time where a happens to have the value 1, it becomes more and more artificial. Then you find that dr is ds.
So the observer.
So, yes, please, make that sentence, please, go ahead.
The observer measuring in a flat space-time at the moment that the scalar factor is 1.
Yes. So it's okay. That's exactly. But there's one extra thing. It's the stationary observer.
Oh yeah, the stationary observer.
The stationary observer.
Yeah.
At the moment that he would measure, at that moment in time, that the scale factor happens to have the value 1, and the space-time happens to be flat,
Yeah.
that is the guy in whose coordinates the Robertson-Walker matrix R is defined. That becomes more abstract, right? Because that is a very fleeting moment, 1 second later, and it
But
doesn't
do we
hold
still
anymore.
take case minus 1 or 1 into
Yeah, can we
account?
still do that?
Since, like, because you said that measurements kind of.
Yeah, well,
So
that
just-
means that in case of a spherical case +1 or a
Yeah.
hyperbolic case -1, there's literally no
Yeah.
observer
Mhm.
in
Exactly.
throughout the space-time who measures dr. Everybody measures some ds, and none of these ds's is dr. That's
But that would
impossible.
make it very special in a way. Like,
And still very special, isn't it?
no, how can I say? That would make it even more special.
I guess,
Yeah.
yes.
I mean, it would
There is
make it.
It just
Like-
means that in a spherical universe, it's not a statement about the universe or the observer. It's a statement about the coordinates in which this particular curvature is expressed. Apparently,
Yeah.
we have expressed our spherical or hyperbolic universe in this particular coordinate system such that none of the observers in that space-time actually measure dr.
Yeah, that could
So
be
dr
possible.
becomes much more of a sort of, mathematical construct for distance than it is actually somebody's distance. This is not uncommon in relativity.
So it's can it be most likely that K0 is not possible?
How's that?
No, I'm thinking more.
Again, the statement that we're now making, that we say there's only one way that somebody would actually measure dr, namely in a.
But it can still occur that we can that's not been measured. That's just
No, but
Yeah.
again, it's not a physical statement. It's a statement about the coordinates in which the metric is expressed. If you could also phrase it like this: we just happen to have chosen very crappy coordinates, in which it just so happens that none of the observers measure this dr.
But then how can you convert other observers to this observer if this observer cannot?
Via the line element. I mean, nobody, if you remember, if you want to convert somebody's distance to some other person's distance, in case of Schwarzschild black holes, you first convert their distances to the bookkeeper observer so you can relate them to each other. You can still do that trick. It's just that the intermediate step of this bookkeeper guy is that the bookkeeper guy doesn't only mathematically exists.
Yeah, doesn't mean as much.
But it's like, because imagine if your universe has a k equals 1. Then you have to go an observer who has a k equals 0.
Why?
Because that's the bookkeeper in our case. He has a k equals 0.
No. Well, yes and no. You can still convert, if you have k is +1, spherical universe, you can still convert some guy's distance to some other guy's distance when both of them first convert their distances to dr. Okay? Now your point is, but in a spherical universe there's no person who would actually measure that dr. That is correct. But you can still mathematically
Go there.
go there. I mean, there doesn't actually have to be a physical person existing in order for you to do that mathematical exercise. I mean, what you can do is that you say, you know what, there's a person A in the spherical universe and he measures some value dA. There's some other guy who measures a particular value B. First you convert this to a dr, then you convert that to a dr, you set them equal to each other, and then you know how these two are related. That's a mathematical exercise you can do even if there's no person actually doing the dr measurement. We were just in the lucky circumstance that in our first example of applying this trick, there was actually a person who measured bookkeeping coordinates. And here nobody does. But you know what, that's not very different from the stuff that you already do in, say, Newtonian physics or electrodynamics. At some point you have to calculate an electric field, right? Is there anyone who ever measures an electric field? What you measure is how much charged particles being pushed around from left to right.
Yeah.
The magnetic field you never measure. It's the magnetic field or the electric field. It's just a mathematical construct that you use as a tool to get to your physical answers. In that sense, this dr is just a mathematical tool to connect physical answers to each other. Again, we're in the happy, very lucky circumstance that the first time that we encountered this, there was actually a person who measured dr.
I think that's the confusing part, that there is now no real observer doing this.
Yes. Unless, of course, and then let's break after that. Unless, of course, you have to be in a Minkowski flat space-time.
Yeah.
Then that observer existed, but only for an extremely
For 1
fleeting
For a
second.
snap of
Yes.
It's still nice to know it was there.
That person existed once
Yeah.
for a very
Once.
short moment of time.
Yeah.
It makes it more abstract, right?
Mhm.
But mathematically, you should have no difficulties relating these things.
We should see it more as a mathematical
Yes.
tool than to convert from one to the other.
Exactly. And we were spoiled in our first example that we didn't have to make it mathematical. Spoiled
At
people
least
is
we know
obvious.
now what we have.
By the way, this is, remember when I started to make lecture, I said I switched around for the practical reasons. The gravitational waves with cosmology, because the gravitational waves has a couple of these abstract steps, and I thought, you know what? Maybe let's do the easy one first. Okay, let's have a break.
It's so warm.
Yeah, it is warm, by the way. We should.
So cool.
What? So warm.
Why
Okay.
tomorrow? Not tomorrow. Don't check it
Just
tomorrow.
don't check it
Just
yet.
check.
Don't check
Okay,
it
thanks.
yet.
Okay.
Yes. So, okay. So people, I think this was very educational, yes? I mean, it gave you a sort of a warning message. Yes, thank you. You sort of a warning message that you always have to find out whose coordinates it is in which you are expressing your motion, because that is now the next step. We can now write down the geodesic equations and solve them in principle. Now we're going to mathematically solve them, and because we now know whose coordinates they are, we also know with respect to whom we now understand the motion, the resulting motion of things in this space-time.
Can I ask you a question in the meantime? Can I ask a question in the meantime?
Yeah, of course.
The metric tensor depends on time, right? The coefficient.
Yes.
So there is no time symmetry in that sense.
That is correct. Yes.
But that means that you cannot extrapolate conservation of energy directly, or something.
That is correct.
So the energy in the whole universe as seen by this guy is not conserved per se.
Correct.
Okay. Isn't that weird?
Because you are seeing energy, the conservation of energy, as a statement that energy, whatever it is, that this is true. Agreed?
Yeah.
Okay. In general relativity, this should be true. Where capital D is the derivative with respect to time, taking into account the time coordinate itself with respect to which you're taking the derivative is changing due to the curvature of space-time. It's called the covariant derivative. Because the reason that this guy that you're talking about doesn't see the energy being constant is not because the energy is not constant, but because the time coordinate in which it is measured changes itself. And that is represented by this covariant derivative. So your observation is astute, and here's your solution. Now, let's write down the geodesic equations. Immediately starting wrong. It should be tau. Okay. Yeah, let's just write them down. Now you tell me we have all the Christoffels, but I just want to make sure that we all are on the same page here. BBL people, I'm scribing. I need somebody else to do the work. I have the easy job here, I just write. It should not be difficult.
Yeah, and just the Christoffel TRR. And then the
R
yeah, the R
squared.
Okay. Yeah, and then the other ones.
and then for the other ones as well.
I prefer writing it in my own notes.
Yes. T r squared sine theta squared d was 5. All of this should be 0. Okay. Wow. Let's Swan-Hughes equation. Well, it's quite a time dilation I see happening here. About the r coordinate. Something is moving through this space-time, or you let gravity do the moving of some mass through this space-time, and this mass, here's the abstract thing again, its location is measured as seen by this hypothetical guy who doesn't exist at one fleeting moment in space, in time, if he had lived in a Minkowski flat universe. Yeah, what can you do? Man, we were so spoiled last week. Alright, so what is man, it looks like quite some complicated motion here. This is not all, read more. We already saw that we can live in a space or in the plane where theta is constant, yes. Newton's killing theorem, conservation angular and blah blah blah. So let's take pi over 2 again for theta. Then you get r sine squared. Well, that's exactly what we did. What else? Oh, by the way, that means that this one is 0.
Yeah.
Yeah, of course. Okay, well, look these up.
It's really picking up scope. It's really picking up.
Anything else? No, sure. The 5 coordinates. Yeah, this one I would like to hear from you, just to see if you're not going to fall into the one famous trap.
R.
1 over
2 over R.
2 over r.
It's the factor 2.
Was that the famous trap?
That is the
Oh,
famous
wow.
trap.
How famous.
The double contraction in the GLS equation tells you that you get R and phi and R, but both give you the same
In my head I
contribution.
was saying that's not the trap, it's something else, something
yeah,
you miss,
okay.
something you don't know. And then I do it.
Oh, you know what? There's another one, and it comes. I'm talking about. I forget where it is. This is the phi. This one. No, sorry, this one. D phi d tau. It comes with a trap.
What a trap. It's my mind.
Just imagine it's not 2 now. That would be
How evil do you guys think I am?
I thought
This one-
it's something that something's going on that it's not the 2 because otherwise, you know, I don't know.
Okay, well, let me
It's like
try
a
this.
double trap, you know.
Let me try this joke one more time, okay? So, there's also one that goes with theta tau, d phi d tau. Yes, this one is 0 because we're going to stick to one plane, but suppose that it's not. There's a trap.
the sign.
The fact that theta is 0? Didn't we decide that?
No.
Theta.
That's what he's just
Yes,
said.
but
The fact that it's really 0 though.
yeah, this is going to be 0, I agree. But suppose that it isn't, okay, there's a trap, an additional trap. Two, okay? This doesn't help.
Yeah, the cosine is theta.
Okay, yes.
Okay.
But it comes with a 2 or doesn't it?
With the 2?
You know, you say it with too much of a question mark and
Because
too
everyone
little
is
of an
quiet and I
exclamation
was
mark.
like in my
No,
head
no,
thinking
no,
like,
no, I'm very happy. Here. It's the same thing, yes?
Yeah.
Okay, good.
Because now you emphasize it.
Yeah.
It's like because you emphasize it, we all
What a
think
trap.
it's not bad.
but
It's very nice.
I really think examiner's going to be like, why do you make
Theta.
things where it's not the
Yeah,
case?
Like, to a square, you
By the
never
way,
know what's gonna happen.
1. 2 pi, sorry, we're doing pi half.
At the beginning I said let's not do the theta Christoffels, because I said, well, we're going to stick to a fixed theta, which is true, but it means that this one is zero, so we might want to take the theta Christoffels. Do we have them?
Anyways, that's true. Would have been 0.
20 minutes.
Do you really take it with us?
Oh, okay, I don't
we
have
have theta.
Okay.
Okay.
Don't turn Christoffels yet, this is time.
For some station you're over 20 minutes, so do we have Christoffels for theta?
Is it just like
it's not really,
It's when
because you can always rotate your reference frame, and then the 2 pi becomes.
theta r.
Because at the beginning I sort of half assumed, well, you know, we're going to stick to a fixed plane, so you might as well not calculate the theta Christoffels. I'm not completely sure that is true, because sure, this is going to be 0 at a fixed plane, but it might be that the Christoffels are not 0, and there's some relationship between these things, so I just want to be sure. So,
Yeah.
do you have them? Or does someone have them?
Yeah.
There's a check going on over there.
So there is theta t theta. So in the sense, the Christoffel was theta t.
Okay, so that will give you this.
Yeah. And but that would be 0 already.
This is 0 for its own reason, but there is a Christoffel in principle.
Yeah.
Sure. Okay. 0.
Then there is
And a
also
factor of 2, by the way.
there is also another one with r theta, and that's also 0.
Yeah.
R.
Okay, because
theta.
okay, so that you also have a dr, d tau, d theta.
And then you
d tau.
have
Oh, wait, I want to make a joke. This is going to be 0. Aside from that, there's a 2.
and then there is phi phi.
And there's phi phi.
Yeah.
That is interesting. Tell me what what the other one is.
Sine theta cos theta. Yeah.
Times cos.
Yeah.
Yeah.
And there's d phi d theta squared.
Squared.
Is
Yes.
0. Okay, so this is 0, that's 0, and that's 0. That's interesting. We have the 4 geodesics now. So wait, guys. This 4 geodesic equation tells you that
It's also 0.
yeah, it is, because we just happen to have chosen this particular plane. If we have chosen any other theta plane, not a pi over 2, which in principle we're allowed to, then you could have seen, well, then d phi d theta itself should have been 0. Do you see that? It just happens that because of our choice of theta, the 4 factor itself is 0, but that was completely arbitrary. So that means that this must have been 0. So whatever the motion is, it could not have swirled with respect to the gas. Right? Remember, all the coordinates are with respect to the gas? Or, excuse me, with respect to the guy who does not see the gas, who is stationary with respect to the gas. So it's also with respect to the gas. Now you see what I mean, right?
Yeah.
The coordinates are in terms of the guy who is stationary with respect to the gas. But since he's stationary with respect to the gas, that also means it's with respect to the gas itself. And the fact that this is 0 means that whatever motion is being dictated by gravity due to the curvature of space-time, it says you do not see any swirling with respect to the gas. So, by the way, that to me, also from a logical perspective, is this completely filled with gas. And the net amount of gas is not moving, which is, by the way, very accurate right now for the air in this room. Okay, the net amount of air is not moving with respect to me. So I am now that observer, and it says that the gravity due to this gas around me is not making me swirl through the room. Well, that's what I expect if there's just the same amount of gas everywhere. There's nothing pulling me towards anything. In fact, doesn't that just mean, guys, that just from a physical perspective, if you are in a room with gas and you are being measured in the coordinates in which the gas is not moving, that you're just not moving, I mean, what is it that should be moving you? Right? If the gas is first of all homogeneous by assumption, right? That's how we got to these equations. So there's just as much gas here as there is over there, as there is over there, as there is over there. Then I find it completely physically expected that mass is put into this gas and not being pulled anywhere. In fact, so we just immediately check whether that is the case. If the solution to this very complicated set of equations isn't just a person who is stationary. 0, 0, 0, 0, 0, 0, 0, 0. It says that this thing, dt d tau equals 0. What does that mean? Constant time relation. Okay. And the time relation is itself apparently determined by nothing. But I mean, there's nothing that says what the time relation should be, or is there? Because what we find, so you all see this point, yes? We have found that at least one solution to the geodesic equation is just masses not moving with respect to the gas. I mean, it literally solves the equations. But for that particular piece of mass within the gas, it says that the time relation with respect to this other person who's not moving with respect to the gas is 0. Excuse me, is constant. So, you have a guy standing here with respect to whom you are doing the measuring. And we found that if that guy looks at some mass and that mass itself is not moving with respect to the gas, how much are these two guys moving with respect to each other?
They're not moving.
They're not moving. Okay, so I would expect that the time relation between them is unity.
Yeah.
Well, that does fit this description.
Yeah.
The dt tau should be a constant. And I expect that constant to be unity. Now I find that it is a constant. If it's not unity, if it's a factor of 2, then we must come up with some reason why the guy with respect to which the measuring is done and this block here that is not moving itself, so we are not moving with respect to each other, still have some time dilation. So if the time dilation is not unity but it's 2 or 500, then I have some explaining to do. These equations do not specify the amount of time dilation. Are we missing something? Why is this system not completely solved? Why do we only find constant time dilation doesn't specify how much time dilation? Are we missing something is my question.
Well, we could still add the normalization.
Yes, and not we
And
could, we should. Every time you solve the geodesic equations, you have to put in by hand the normalization of formulas. You can already see here, we saw last week that we had too few equations to solve the system. In this case, we also have too few equations. So let's do that right now. We have found that masses in this Friedman universe are not being pushed or pulled anywhere. They just stay stationary with respect to the gas. It's a mathematical solution, it makes physical sense, all good. But we do find that there's some possibility of some time dilation. It's constant, but it's not necessarily 1. So let's check what that time dilation is. So you tell me. Simon came up with the brilliant suggestion, no sarcasm here. Put in the conservation of 4 velocity. You should always do this by hand. Let's do it right here, right now. That means the contraction of the 4 velocity with itself should be -1. Okay. So we have to write out the left-hand side, agreed? Okay. So the u mu we already saw should be that block that is not moving with respect to the observer. So that means that most of these 4 velocities are going to be 0, agreed? Okay. So I think that this double contraction will only give you, these 16 terms will only give you 1 overall term. Which one is that? Mu equals which coordinates?
Only the T1.
Only the T1. Right? This is the motion of that mass that you're looking at, which you are normalizing. With respect to the gas, we saw that. With respect to the coordinates in which everything is expressed, and we saw that was the person who was stationary with respect to the gas. We saw here that that mass itself is not moving. That means all the spatial 4 velocities are 0. The double contraction here tells you you only have to take into account the TT1. So I get GTT UT squared. What is GTT? For the Robertson-Walker method.
Oh. -1.
It's -1. Sorry. And the normalization says, well, that number UT squared has to be 1. So
dt d tau. Yeah.
So we find the dt d tau should be 1. And this is exactly what we expected on physical terms. So it's good to see that everything lines up. So, I'm very happy. Looks nice. It works out. Now, to make a suggestion in your own home studies, there's lots of principal understanding that goes with this exercise. Yes. So I really feel that this is something that you should really understand. Do not memorize this by heart, but understand what went on here, why we asked the questions that we did, and how we solved them as we did. So.
Is this tensor also in the book?
As
well,
yes, there is. It's chapter 18 or so. But it so happens that I myself wrote lecture notes on this many years ago, maybe 15 years ago, which gives you well, I'm going to put those online so you can read those for yourself. I'm not saying that it's better than the book, but it does explain all of this in detail. Okay. How are we on time?
10 minutes left.
10 minutes! Oh wow!
You did well this time.
Yes, yes. I'm super happy.
Yeah, but in the lecture it went.
No, that is true. But we also started 15 minutes later with the tutorial, so that means I actually get my 10 minutes now. So I'm basking in my 10 minutes. Big amount of time. Right.
Is there anything you can do within 10 minutes? Don't want to go overtime now.
Yeah.
I'm sure you will remind me when we get there.
You wrote those 15 years ago?
And then again, thank you for indulging.
2003,
No problem.
So you were teaching this 15 years ago already?
Yes, okay. Well, here's a way that we can fiddle for those 10 minutes. Yes, I wrote those in 2003, the lecture notes, and the reason that happened was I was still a student back in the day, but my professor was teaching general relativity and cosmology. There was a course called Gravitatie and Cosmology.
A PhD student?
No, there was a professor of physics. He was later.
No, by you.
I was later going to be his PhD student, but I was a non-PhD student also, like you, when I was following the course myself. But I was. I don't know if it sounded too way out there or too way low down there. I don't know what image I conveyed here.
It's okay. It's okay.
So no, we had he was teaching general relativity and cosmology this course, and I was his teaching assistant, so I was doing the tutorials for that. But it so happened that he had to have some medical thing that he had to go through. It wasn't nothing serious, but it took him out of giving classes. And then he asked me, well, we can ask the students to study this on their own, and you just do the tutorials with them. But I like to teach, so I said, you know what? I was going to do the main lectures, and then I wrote these lecture notes for this, which was highly educational for me because I had already passed the course. But then you really have to think about it a little bit extra. And he didn't know that, by the way. He thought I was just going to do the tutorials, and I secretly gave the full lecture course, including the tutorials. It was one of my proudest moments. I'm not saying that it did well by now, but it did leave me with full lecture notes that about. So that's anyway. How was the time?
7 minutes.
Oh wow. My oh my. I see that too. Yeah.
Okay. In all seriousness, I do think that we're not going to do any more quantitatively, but there's 2 more exercises that go with this. Maybe we can just discuss how you could solve them. Okay. What we've now done is that we have taken a particular solution, namely that masses are not being pushed left or right by this gas in which they float about. Again, that makes sense. If there's just as much gas here as over there, then gravity does not have any reason to pull you anywhere. But that also means that in principle you can give a mass just a little push through that gas, and well, again, as the mass is floating about, there's nothing in this direction or in that direction that gives it any preference to go faster or slower, so you'd expect sort of like Newton's first law to hold there, except for that passkey, A is a function of t, agreed? And not just that. It, in principle, depending on your value of k, it's also a curved spacetime. So in a Minkowski flat spacetime, you would expect the mass that you start with a constant velocity not to accelerate. You would sort of have Newton's first law, but in an expanding spacetime. But in a curved spacetime, where k is not 0, you might expect something else. Can you guess what that's going to be? Suppose if you have a spherical Robertson-Walker spacetime, and you have a mass and you give it a little push. What will happen to it? How would its motion look? So you're moving on a spherical spacetime. The surface of the spherical spacetime.
I mean, it will
slow down.
Will it slow down?
Why?
Why?
there is
We'll
no
come back
friction,
to
there
its
is no.
starting
Yeah,
point.
sure. I was thinking because the space expands around it, so you would assume that
Okay.
you know relative to your measuring.
That makes sense.
There's a good point there, because if you think again about this,
Yeah.
well, let's take the balloon example again, right? So it's like moving on the surface of a balloon, but while something is, let's take an ant, no, let's take a ladybug, let's take John. Suppose if a ladybug is walking on the surface of a balloon, but while the animal is moving about, you are blowing up the balloon very slowly, so he doesn't get disturbed. Then what you expect is that he still keeps on moving. That's fine. It's just that it takes longer for him to get to the next grid point, because the grid points while he's walking are moving away from each other. So
Yeah, in that sense.
in that sense, you would say he's slowing down.
The grid lines.
Yes, but and now we have to be careful again, because is anyone actually measuring grid points distances in that space-time? We had a very big discussion on that.
No, but you would assume that the distance between the things on the grid points also
Well,
gets bigger.
yes, but there's really something that you have to do here. So, by the way, my claim is that if you take the geodesic equations and let's suppose that you are walking at a fixed theta and a fixed phi, just as we saw that this already said that you should move at a fixed phi. That to me, by the way, sounds that you're moving in a straight line. If you're not making any curves, because theta is constant and phi is constant, you're moving in a straight line. But then you still have to ask yourself, okay, but what is your distance that you travel? Now, you tell me, how do you calculate a distance traveled? If you have your line element. Yes, a little bit more.
The square root
You have to take, yes, you have to integral the square root of your
of the line element.
So S is going to be the integral of this, which is the integral of the line element. You have to take dt is 0 because you're measuring a distance. We also said, well,
Just a straight line.
we're a straight line, so let's make a straight line in a radial direction. This frequent equation, this geodesic equation already said that phi should be constant. Theta can be taken as constant. So that means that the only term that appears here is the one that goes with the radial one. And that is 1 over x squared, 1 minus kr squared. And the dr drops out, gets outside of the square root. This is an actual physical distance that you measure, agreed? We already saw in the discussion before the break that nobody does the measurement of dr. If you want to know how fast something is moving, then you have to take this number and divide by how long it took to take that time. Now Felix's point was, well, wait a minute, this ladybug on this balloon that's blowing up, the grid points get further and further away from each other, that's true. But nobody is measuring the distance in grid points. People are measuring, this is measuring in grid points, people are measuring this. And then you see, oh, but wait a minute, this thing comes with its own little scale factor. So he does not slow down.
Okay.
Yes? It's a very important point here. We concluded that nobody in the space-time measures dr. if you want to know what people actually measure, as in that if they would take out their measuring stick and they would see how many meters somebody travels, that in this case would be this expression. And then you see that it also becomes bigger.
Okay.
So the grid points get further and further away from each other, that's correct. But the distance also gets further away from each other, so that means he does not slow down. So that to me sounds like constant velocity. Or is it? Because this A comes, that changes in time. So distances traveled could actually increase or decrease depending on whether that space-time is moving or increasing or not. To me, that also makes sense, because look, let's take, instead of a ladybug, let's take me, and let's take this floor here as being the space-time, the Robertson-Walker space-time. It's not spherical, but a point still holds. I'm happily moving my weight here, okay? While at the same time, space-time, so the floor is being stretched out to both sides. That means I'm being swept along with the underlying space-time, agreed? Mm. So, there is a version of Newton's first law going on. Things do move in a straight line, according to the geodesic equations. But the thing on which they are moving is itself stretching out, which effectively, by this equation, means that they are being swept along. Now, replace me or the ladybug by actual galaxies in the universe. If you go and take your telescope out and look at galaxies in the universe and you see that they're moving away from us, it's not because they are in space-time and they're moving on the space-time with their own little push that they got from somebody. No, they're being swept along with the underlying space-time itself. Do you see the difference between those two statements? So, the expansion of the universe you can measure by looking at galaxies, all the space-time, that as the space-time underneath is stretching out, the galaxies are being swept along. This is how this is measured. This is how Hubble in 1929 did his measurement of the movement of the space-time. Of course, what the space-time, or what the galaxies also do, is that they might be moving about themselves on that space-time. That's what we call peculiar velocity. Mm-hmm. Now, those motions are typically very small if the galaxy is very far away, because whatever motion they might have is completely swamped at a large distance, right? It's hard to see something move, it's very far away from you. But if the galaxies, the closer the galaxies are that you look at, the more you find that they don't really follow the expansion of the space-time. Well, that's obvious, because they are being swept away along with the space-time, but on top of that they are close enough that you can actually see the peculiar velocities. So, what does exercise D and E ask of you is, take two of these galaxies, or two of these ladybugs, or two of these lecturers. Let them start close to each other, both give them a push, and check how they move with respect to each other. We see now that they both will move in a straight line, but how they move with respect to each other. You will find, I've already given you the answer, that for k is 0, they keep on being parallel. They're being stretched out both as they go along, but they stay parallel. In case of spherical, you will find that they're also being swept along with the increasing space-time, but they get closer to each other. Just as two ladybugs on a sphere are going to find each other at the North Pole, even though the sphere itself is blowing up. And a hyperbolic means that the two ladybugs will move away from each other. So exercise D and E ask you to do this exercise. Check for yourself that the k is 1 indeed agrees with what you would physically expect for things moving on a sphere. And k minus equals -1 for a thing moving on a hyperboloid. Okay guys, I think we're now...
3 minutes over time.
Okay.
You did it!
Yes.
It's exactly the 3 minutes you spent on the story.
Okay.